Hi, I am recording this video after class because the lecture recording that I did during class failed. It was a technical error on the software, so I'm going to do this one over again just to make sure that the stuff we did in class today is available on a video in case you need to consult it again. So I'll just review the announcements quickly. First of all, the next homework assignment, homework 5, that's due on Sunday. So feel free to stop by my office if you have questions on that, or if you'd like to send me emails during the weekend, I'll do my best to respond to those. Also, we're going to be back in the computer lab again on Thursday. So today, in the in-class exercise and the questions that we go over, I'm going to demonstrate how to use the computer to find the present value and the future value of some complex cash flows. And then there's also a paper method problem at the end. When we go through the spreadsheet today, you're going to see once again the PV function. So you've seen that in the previous class, how we use the PV function. And the FV function is similar. For the FV function, once you start typing it in with equals FV and then the parentheses, suddenly Excel knows that you're doing a function and it'll begin to prompt you with the things that you need to add. And so in the first field you'll put the interest rate expressed as a decimal. The next field it will say NPER. What it means from that is what is the N value that you need. In the case of the future value, it's asking how many years do you want to take this amount that's currently at the present into the future. And so N isn't necessarily what row you're on, but rather it is how far into the future you're taking the present amount that you enter later on in the formula. So that's what N is. Remember, the next thing we do is we put in 2 commas. And the reason for the 2 commas is that you're skipping over the payment field. The third function, the third field that it's going to ask for in the function, payment, the only reason you'd put something inside of these commas is if it was a recurring amount that's always the same and you're trying to take that into the future. But the way we're going to use the function today is not a recurring payment that's the same amount for a certain number of years, but rather we're going to be taking amounts that are in a present and we're moving it forward into the future. So that's how we're going to use it, and just remember that the sign change occurs anytime you do the PV function or the FV function, and so we have to put a negative value before that present value or the future value in order to preserve whether it's an inflow or an outflow. There's also a function that I'm going to demonstrate called the net present value function. And net present value is a little bit simpler than calculating the present values on a row by row basis. And it works great, but you don't really get to see each of the individual amounts. It calculates everything all at once and automatically adds it. One important warning to give you, and I can emphasize its importance by pointing out this is underlined, bold, and in capitals. Only put future values into the range. You don't include something that's already in the present in the NPV function. All right, so let's test some of this out with the following cash flow diagram. We know that there's going to be some money coming to us in years 2 through 5, again in years 8 through 11, a single payment in year 13. We're going to have to pay a small amount in year 14, and then in year 16, it's another cash payment that's coming to us. You can see that the A means that, and you can imply it from the arrows all being the same height, that these amounts are consistent. And then we have these individual future amounts that we're also going to try and take to the present. So the word discount, we're going to discount these to the present. That means we're taking some future amount into today's terms. We want to know if we were going to receive a single lump sum today in year 0, what is the value of that lump sum if we're discounting things at an interest rate of 7%. So we'll start with A, using the present value function with Excel. So here I've got Excel open, and I'm going to translate the cash flow diagram. Let me just copy it and paste it so that you can see as I translate it into the table what I'm doing here. So the first thing is I'm going to be adding a column that I call time, and then amount, and then the PV of amount. Now up here, I'm going to define the interest rate. So I equals, and I'm going to tab over to the next field, and for this one it's 7%, so 0.07. All right, so the time is just how many years we need to go through 16 to get all of the cash flow amounts into our diagram. And then the amounts are going to just correspond to how much is in each of them. So far we have 0 that's coming to us in year 0. We are going to solve for what is the equivalent present amount, but you can see that there's no actual cash flow in year 0. It's just this dashed line. There's also nothing in year 1, but in year 2 it's 12,500. Okay, now it's telling us here that the currency is dirhams. So what I'm going to do is I'm going to highlight these and I'm going to change the currency type to dirhams by scrolling down here in these options and have it say AED. If I go far enough down, I think I'll get to the abbreviations. Oh, I just passed it. All right, there it is. So now it's knowing that each of these are dirhams, and I'm going to say currency. I'll undo that. All right, so for the next one, it is 12,500 for 4 years, so that needs to be including through year 5. In year 6, there's nothing, 7. In year 8, it's 15,000. And I'll drag that down so that there's 4 of them. There's nothing in year 12, 17,000. In year 13, year 14 is negative 7,000. Nothing in year 15, and then 8,000 in year 16. So there's my cash flow, just translated from a diagram to a table. Now for the present value of the amount, I want to move all of the future amounts into the present. So to do that, I'm going to use the function equals PV. And for the rate, I'll just click here where I've got the rate indicated in the cell. I could type it in, but it's better if you just click on this location, because then I can change that location, that one amount, and all of them would change if I needed to see what's happening with a different interest rate. So that's why I click in that location, and then I'm going to press the F4 button to put the dollar signs in front of the B and the 1. So I've just pushed that button, and that's called anchoring it. And the advantage of anchoring is that it always looks in the same cell. Even when I apply this formula by dragging it down to different rows, it's always going to look in the same location for the interest rate. And if I didn't anchor it, it would start looking lower and lower for the interest rate, just depending on how far down I dragged it. Okay, N is this, which is how many years I have to move it from its future amount to the present. So 0 is already at the present, 1 means I'm moving it 1 year, from 1 to 0, and so on. So I put in a comma, now it's asking what is the recurring payment, but this isn't a recurring payment. Each one of these rows represents a single one-time payment. So I'm going to skip over the payment field. Now I'm in the future value field, negative of the amount that's listed there. And the negative is because Excel, for whatever reason, automatically changes the sign when it converts between present values and future values. I think it's assuming that if you make some deposit now, you'll be making a withdrawal in the future, so it's trying to force that directionality on you. But in my case, I don't want it to do that. So if I drag it down, what we'll see, for example, is that 8,000 dirhams in year 16, if I'm discounting it at 7%, it's only worth 2,700 dirhams in today's terms. And so that makes sense to us. Remember, we've said that money in the future is less valuable than money in the present. And so 16 years in the future, that 8,000 dirhams isn't really worth much in today. So what is the total present value of the entire cash flow? If we're going to take all of these future cash flows at once in year 0, what I do now is I sum the entire range and find that the value of it in today's terms is 78,000 dirhams. And so I can take this amount, or I can take the future amounts, but at 7% interest, they're equivalent. So that's the answer to our first question here, using the PV function what is the present value. Now the second approach is using the function NPV. And so let me show you how that one works. Here I'm going to call it the net present value. It's going to be the same amount, it's just a different way of calculating that same amount. So I do this function equals NPV, and it wants to know the interest rate that it should be discounting at. And the interest rate is 7%. Now the amounts that I should put into this function should only be amounts that are in year 1 through 16. In other words, if there was an amount already in year 0, I don't want to include it in the function because the function is thinking in its mind, convert things from the future to the present. And whatever amount is in year 0 is already at the present. So therefore, I'm only going to select these amounts that are from the cash flow diagram. I don't want to accidentally select the amounts that are already converted to the present, but this is sort of the raw data that I've selected. And when I close the parentheses and press enter, then it tells me the amount. Now it's reporting it as dollars, but it's dirhams. The amount is 78,260. So the net present value function, what it does is in it, Excel already can know that whatever I selected first was in year 1, what I selected second was year 2, what I selected third was year 3. So it's sort of building in all of what we did manually through calculating this column. And it finds the net present value. So that's the solution to the first one. All right. Let's take a look at the second question. The second question in the activity is asking, for this cash flow diagram, we want to move all of the money that's shown into the future. And so that's compounding it into the future. For example, $10,000, if you receive it today, how much would it be worth in 16 years if it was increasing in value by 8.5% per year? And so a deposit made in year 0, you're earning interest on the interest. So it's compounding until it gets to year 16. This amount in year 2, it doesn't have to travel as far. It's only going from year 2 to year 16. So how far does it have to travel from year 2 to year 16? Well, that's 14 years that it's moving. This 11,500 in year 3 is only moving 13 years. And so here where it's saying use the following columns, and I'm telling you what to put into your spreadsheet, I've put this thing here, years until year 16. And the reason we want to have that data is that's going to be the n that we use in the future value function. So let's give that a try. Let me pop open another window here in Excel, and I'll paste the cash flow diagram just so we have easy access to this. We're on ICE 11, problem 2. All right, so here we have the interest rate, I, and in this problem it's stated that we should use 8.5%. And now the column titles that I've asked you to add are going to be year, years until year 16, amount, and future value. So year, years until year 16. And then the next one is amount and future value of amount. All right. I'm going to make this column a little bit wider so I get the whole title. Same thing here. All right, so year 0, 1, 2, and so on. Drag this down so I can have it go through 16. All right. So how many years is it until year 16? If I'm moving something from 0 all the way to year 16, then that's 16 years that I'm moving it. If I'm moving something from year 1 to 16, that should be 15. So I could type it in manually, but maybe a better way of doing it is with the formula. Equals 16 minus, and then whatever year we're on. And if I drag that down, then it knows that in year 15, I'm only moving something 1 year, and so on. So I hope you get the idea about what the secondary time column is all about. And if it doesn't make sense yet, I hope it will once we start doing this future value column. Okay, so now I'm just going to put in the amounts, 10,000, 0 in year 2, it's negative 11,500, and we're going to have a couple of repeats of that so that it goes through year 5, and then we have nothing in year 6, 15,000, and there are 3 instances of 15,000, nothing in year 10, 17,000 in year 11, nothing in year 12, in 13, negative 7,000. Another one of those, nothing in year 15, and then year 16, there's also nothing there. We're going to be moving everything to year 16, but there's nothing currently in year 16. All right, so we know we're going to use the FV function, equals FV. And the interest rate that we're using, we click here in this cell, and remember that the purpose of anchoring is that if I didn't anchor, once I drag this down, it always will be looking, it's called a relative reference. So that if I didn't anchor it and I drag it down in one place, then it's going to look in this cell for the interest rate. And the interest rate isn't in that cell, it's only here. So by pressing F4, or you can manually type in these dollar signs, what that does is it tells this function, when you copy the function and repeat it, to always look in this location for the value that's corresponding to the rate. Okay, so N is how many years it's moving into the future. So I'm using this because whatever amount is in year 0, I need it to move 16 years to get it to this final point here at 16, year 16 that I'm interested in. So you can see I'm going to use this column for time, skipping over the PMT because that would imply that this is always 10,000 all the time, 16 times, but it's not. It's only a one-time instance, and so this 10,000 is in the present. So I'll do negative of this amount. So if you move that amount into the future, then it's worth 36,000 versus the 10,000 that it's worth today because of the compounding. And when I drag this formula down, it's going to apply the same logic to everything. You'll notice that the 7,000, for example, in year 13 has a greater future value than the 7,000 in year 14. And the reason why is it is compounding a greater number of times. And so the further in the past it's compounding from, the greater effect it will have in the future. So now here I'm going to calculate the total future value by using the sum function, and I'm just going to select all of them. I'm pushing the shift button and scrolling up, and then enter. I don't even have to do that closed parentheses. Excel knows. So the total future value is 3,820. There isn't a net future value. Well, actually there might be, but NFV? No, there's not. I was wondering, maybe they added a new function I didn't know about. So this is how we've calculated the future value of all of this cash flow in terms of year 16. All right, let's look at another problem. How to calculate the rate. You know, here we've already got a cash flow table. So we had a cash flow diagram, converted it into a cash flow table. We want to know if you made a deposit of $45,460 in year 0, and then you withdraw $7,500, this equal amount. If you keep taking it out 7 times, what interest rate do you need so that this cash flow is in equilibrium? In other words, that means that when you take this last deposit, when you withdraw it from the bank, that means that the account is empty. So you put money in one time, and then you take out all of these recurring uniform amounts. What interest rate is needed so that there's enough money on that last one to give you your $7,500, but then there's nothing left in the account? So this one's relatively simple. I can copy this just for reference purposes, but I'm not going to actually solve this in a tabular way. I'm going to just enter in the rate function, and let me zoom in so it's a bit easier to see. The way I'm going to do it is just equals rate. Now let's look. How many payments of 7,500 are there? There's 1, 2, 3, 4, 5, 6, 7. So I'm just going to key in 7 payments. And now the amount of the payment I can see is 7,500. It's going to ask next, what is the present value? Well, this present value, the amount of my deposit is negative 45,460. And then I close parentheses, press enter, and it says you need to have the account making 4% interest. And I can show more precision by increasing the number of decimals that are shown up here in the ribbon. So once again, let me explain the interpretation. What that means is you put in 45,460. That's the amount of your deposit. You start taking out these withdrawals, and at the end, there's nothing left as long as the interest rate that you were earning on the entire time was 3.735. And so just for kicks, I didn't do this in class, but let's see what is the account balance if I do this. So here I've got my account balance is that. So now the next year the account balance is 1 plus I times the previous year, because I'm earning interest. That's what the 1 plus I is about, and I'd better anchor that if I'm intending to drag down. So the 45,000 that I deposited has grown. My deposit is now bigger. And then also, though, I want to take my withdrawal. And so now if I do the same procedure, what I hope to see is it will go to 0 at the end. And 5.9 times 10 to the 10th is basically 0. So it works. It means that the last withdrawal, when you take out that 7,500, after doing that, there's nothing left. That's how you use the rate function in Excel. All right, so the last thing isn't an Excel problem. This is kind of a hand problem. And I bring it up because we're going to start looking at complex cash flows that we have to do in multiple steps. And so let me break down what we're looking at. We have, first of all, this 1100 is an annual series, also known as uniform series. And then in years 4 through 7, there's both a uniform series and a gradient at the same time. So we'll break that into pieces in the same way that we've broken this into pieces in class previously. The first thing I'm going to show is how you'd take the 11,000, 3 payments of 11,000, and move it to the present. And because of the form of how we shift a uniform series, you have to treat the first year before the uniform series begins as a quasi year 0. So in other words, even though the annual series starts at year 2, goes 3, 4, and 5, now this is year 1, but we're going to pretend like it's year 0 from the perspective of this annual series. And so the perspective is going to give us sort of like a pseudo 0 at year 1, and then we would have to move it 1 additional year. So let me bring up the solution to show you what I have in mind for this one. All right. So the first step, you can see this 11,000. We're moving the 3 payments of 11,000 to year 8. And so the A is 11,000, moving it from 9 through 11 to year 8. Now the function we would look up in the back of the book for whatever interest rate this is. Now there's no interest rate specified. It's just a conceptual problem for now. You do a P/A. P/A means find the present given the annual that's known. So we'd want to find out how much is all of that worth in year 8, and we'd use that factor to do it. And then we would move it from year 8 over to the present, which is here at 0. And so see, I'm labeling it as A and B. So I'm saying once you transform this big amount in year 8 over to in year 0 terms, since it's been discounted, that's why I drew the arrow as a little bit shorter. All right, the next part of the problem is what we're going to do with these outflows. We've got an annual series of 500 each year, and then a gradient, G equals 100, as the amount is increasing. So from the perspective of the annual series, our 0 year, or the quasi-0 year, is here at 3. Because when you're moving an annual series, when you're doing a P/A, you move it to the 1 year before the first amount you see. So here was the A at year 4, 5, 6, and 7. You're moving it to year 3. So you can see that the function I've said here is do a P/A for whatever the interest rate is, and n equals 4. There was 4 payments, 1, 2, 3, 4, and those are transformed into some contributor at C. There's 2 things that are going to go into C. There's going to be the A part of it and the G part of it. So the next step is moving the gradient of 100 from years 4 through 7 to year 3. And in the same way, we do a P/G at I%, n equals 4. We'd look that factor up out of a table, multiply it by 100, and then it would tell us the amount that is at 3. And then the final thing we have to do is take the whole amount, all of the amount that's at C, and move it to year 0, and that's what I'm calling D. And the function that we would use is a P/F. So we're pretending like it's in the future. We want to find the present value of it. We do it for 3 years. And so the total present value of this cash flow diagram would be the net difference between B, which was our inflows, and D, which was our outflows. So we're going to do a lot more of these complex cash flow diagrams in the future. So if this doesn't make sense to you yet, it will, I hope. There's definitely some good examples in the text that can give you extra practice at breaking these down into pieces. So before I finish up, let me just take one last look at the announcements. The homework assignment that's been handed out in class, and it's also posted on iLearn, that's due on Sunday, February 28th, and we'll be back in the computer lab on Thursday.